This is the first video for chemical bonding. In general, we have 3 goals that are listed here for Chapter 6, and they all focus around chemical bonding. This video will focus primarily on ionic bonding. But before we get into different types of bonds, we have to understand why atoms choose to bond. Now, if you remember from the last chapter, there are only 6 elements on the whole periodic table that are already stable, and we call those the noble gases: helium, neon, argon, krypton, and xenon. And those elements are stable because their outermost electron shell is full. We can't fit any more electrons. Every other element on the periodic table is considered to be unstable because they do not have a full outer set of electrons. So in order to become stable, atoms choose to bond. They can bond by either gaining, losing, or sharing electrons with other atoms. There's a rule that helps us remember this, and this is called the octet rule. The octet rule says that every element would like to have 8 outer shell electrons, with the exception of hydrogen and helium. Because they are so small, they can only have 2. But if they have 2 electrons, then they are considered stable. And you might recall from last chapter that we draw electron dot diagrams. So you'll need to recall from your periodic table, which you might want to go ahead and take out, that we have patterns of valence electrons. So when I look on my periodic table, I can remember that hydrogen has 1 valence electron, lithium has 1 valence electron, carbon has 4 valence electrons, and fluorine has 7. Now you'll notice for all of these, none of these atoms, none of these elements has a full set of valence electrons. So all of these elements listed here are unstable. And so in order to become stable, they want to bond with other atoms. In this video, we're going to focus on ionic bonding. Ionic bonding is when atoms lose or gain electrons. The other video that you'll watch is over covalent bonding, and that's when those outermost valence electrons are shared between elements. There's also a third type of bonding called metallic bonding, which we'll end up the chapter discussing. But for each type of bond, we'll learn how the bonds form, the properties of each bond, and how to name that specific substance with that bond, because there will be different rules that we need to follow. So let's talk about ionic bonding. So ionic bonding is when electrons get transferred from one atom to the next. So if you see here, you might want to write this sample down, pause the video, and we're going to write Lewis dot structures for sodium and chlorine. So sodium has 1 valence electron. And if I look on my periodic table, chlorine has 7. Now based on the octet rule, neither one of these elements is stable. Sodium has 1 valence electron, chlorine has 7. In order to become stable, sodium would like to have an electron configuration like the noble gas that comes directly before it. And if you look on your periodic table, you'll see that that's neon. Chlorine would like 1 additional valence electron to have 8 to be like argon. So this is actually what happens. Sodium has this extra electron, chlorine wants another one, and so what happens is that this electron from sodium gets transferred over to chlorine. And when that happens, we get ions forming. Sodium, because it lost an electron, becomes a positive ion, or what we call a cation. Chlorine now has an extra electron, and so it has a negative charge, which we call an anion. Now we know what happens when we have opposite charges. We have an attraction that can occur. So once we have this transfer of electrons, ions are formed, and then those ions are now attracted to each other, and we get the formation of an ionic bond. If we take another look at what really happened, here are some Bohr diagrams of sodium and chlorine starting out. And you can look, here's the 1 valence electron for sodium in its outermost shell. Chlorine has 7 valence electrons in its outermost shell. Both are unstable. You can see this electron gets transferred from sodium to chlorine, which would be this electron here. And when that occurs, sodium has become a positive ion, chlorine has now become a negative ion, and those ions are attracted to each other. In fact, they're attracted to each other in what we call a three-dimensional structure called a crystal lattice, and we'll talk about this structure in just a moment. So in general, ionic bonds are caused by the electrical attraction between cations and anions that form when electrons are transferred from one atom to the next. And there's a couple different representations of those crystals here. Because of this crystalline structure, we have some unique properties which you'll need to record. So that attraction between the cation and the anion is very strong. So we have some unique properties, one being high melting point, so it takes a lot of energy to break those bonds. Ionic compounds are also brittle, and you can see here in the diagram they're brittle because of this arrangement of positive and negative ions, and you have to imagine this in a three-dimensional structure. And if I hit a crystal, if I hit an ionic compound, it actually shifts these positive and negative ions. And so what happens is if I push here, the positive ions end up being by themselves, and we know that positives don't like to be by positives and they repel each other, and so we get an area that will shatter. We'll get this fissure line right here. Other properties that you need to know is that solids, ionic solids, are not good conductors of electricity. However, if I melt them into a liquid, or if I dissolve them into a liquid, they become very good conductors of electricity, because as you know, electricity needs positive and negative charges to flow in order for the electricity to flow. So we can kind of look at this cartoon here. If you read the bottom part, it says, perhaps one of you gentlemen would mind telling me just what is outside the window that you find so attractive. So we see these positive ions and we see these negative ions. Well, how do we know what elements are positive and what ones are negative? Well, this all goes back to your periodic table, and that there is a pattern on your periodic table. And if you recall valence electrons, for example, the elements in group 1 have one valence electron. Every element in this group likes to give away that one electron so that they will be like the noble gases. They would have a stable structure like a noble gas. So the result is all of these atoms, these elements in group 1 tend to have a positive 1 charge. They like to lose one electron. Elements in group 2 have 2 electrons that they like to get rid of, and so they have a positive 2 charge because they get rid of 2 electrons. And if we continue on with this pattern, if we skip all the way over to the other side, to the boron group, atoms or elements in this column tend to have a +3 charge because they give up 3 electrons. Then we have a plus or -4 for the carbon group. These elements like to either give up or gain 4 electrons. The nitrogen group likes to gain 3 electrons to become stable. The oxygen group likes to gain 2 electrons to become stable. And the halogen group likes to gain 1 electron in order to become stable. Now the charge for the noble gases is 0 because they do not like to gain or lose electrons. They are already stable in the way that they are. Once we have this pattern down, what we now can do is we can write formulas for substances that have ionic bonds. So I've got the simple rules here. I'm just going to walk through a couple samples for you. So we use our periodic table, and when I ask you to write, let's say, a formula for sodium chloride, table salt, I go to my periodic table and I write the symbol and the charge for both of these ions. So here we go. So sodium is Na. It's in group 1. It has a +1 charge. Chlorine, which is the ion that chloride comes from. Chloride is the ion form of chlorine. I look on my periodic table and it has a -1 charge. Our goal is to have a neutral atom. So what I'm going to show you will work every single time. This is called the crisscross method. Drop the charge. So I'm just going to circle the numbers of each of those charges, and I'm going to cross them down, and the charge goes down and becomes the subscripts for the other atom. So this actually would look like this originally: Na1, Cl1. I have to do a couple things. First of all, I never write ones in chemistry, so I just assume that those each have a 1 subscript. Now, if I were to have crossed something over and it would have looked like this, let's say Ca4O2, I'm making one up. If I cross those numbers down, I always want to make sure I can't simplify these just like I would simplify a ratio. Well, a 4:2 ratio would simplify to Ca2O. 1. There's an understood 1 there, but we never write 1 subscripts in science. So this method of finding the charges for each ion, crossing them over, works every single time when you are asked to write a formula from an ionic compound. Now we could also do the opposite. We could also be given a formula and we are asked to name it. And if you look here at the rules, it's very simple. We look at the first element, and all we do is we write the element name down right from the periodic table. The second element we write down, but we change the ending of the element name to "ide." So if we do this first one, Na is sodium, I is iodine, but instead of writing iodine, I'm going to change the ending to IDE. So this ends up being called sodium iodide. K2O, the numbers don't matter. I'm going to name the first element potassium. The second element is oxygen. Oxygen becomes oxide. And this is how we name substances that contain ionic bonds. Now, so far, we've only looked at elements that are in what we call the main group, the ones where we have written the charges on. We've actually ignored all of these transition metals because they're a little tricky. Transition metals are unique in that they can actually have different charges. So, for example, iron, which is a transition metal, can have a +2 or a +3 ion. So we have to name them differently. So in their names, we have to put the charge in parentheses as a Roman numeral. So if something contains the iron +2 ion, we call it iron Roman numeral 2. Iron with the +3 charge, we name it iron Roman numeral 3. And you can see the pattern there. If you need to stop the video and rewind it, be sure when you come to class that you know the rules for naming and writing formulas for substances that have ionic bonds. You also need to know how to find the charge from your periodic table.